Let's look at our trig functions in particular. Remember our basic sine curve. So when I'm drawing up my basic sine curve, I know it goes between -1 and 1, so I'll put that on the y-axis. I always like to plot in the boundary values, so every 90 degrees, but of course now we tend to use radians rather than degrees. So we've got pi there, 2 pi, 3 pi, and I've gone back the other direction a few as well. If I have to draw the sine curve, when I'm plotting them I go, where does it start? Well, I know it starts at 0. A sine curve will start at 0, it goes up to the amplitude, and then I know the pattern, it goes down and up, and so on in both directions, and then we draw a nice smooth curve between them all. So that's our basic y equals sine x. What do we know about it? The domain is all real x, there are no breaks in it. The range, it goes between -1 and 1. Now I can do some shifting on this now. So if I was to do all the different things possible, I might put a number in front of the trig function. So in other words, it's the same as saying y over a for the dilation, but I could do that. So I've got y equals a times the sine, and inside there I could dilate the x as well. So I've got bx, I could put a shift on it, minus c. I suppose technically I could have gone plus another number too, because I could shift the whole thing up and down as well. The period of a trig curve is how long does it take until it repeats? I mean, that's what period is. Our lessons, we're having periods. So how long does it take to the next period? Well, every period's 40 minutes. That's the period we have. Well, trig curves are the same. The thing you have to remember with a trig curve is it's not just when it's at the same point, also travelling in the same direction. So you could make the mistake of saying, hey look, I'm at the origin here, so I'm at 0. Oh look, I'm back at 0 here at pi, so the period's pi. But not true, because at the origin I'm going up, but at pi I'm going down. It's not until I get back to 2 pi that I'm going up again. So the period is 2 pi. To generalise it, it always turns out to be 2 pi on b, because what effect does that b have? It's the horizontal shift. So it's going to change the period, change how long it takes for it to repeat. The amplitude of a trig curve is how far up and down it goes from the centre or the axis of our curve. So our standard one is 1, but it'll always turn out to be a. Whatever a is, okay, that's to do with the vertical dilation. So we're stretching it up to a. Another useful thing, when I'm drawing mine then, whatever the period is, I'll mark off whatever that period is divided by 4. Because that's going to give me the boundary points that I can plot to draw my curve. So I always draw my divisions, whatever the period is, divided by 4. Phase, well that's talking about the shift, or the horizontal shift of the curve. It turns out to be c divided by b. Because when you're looking for the shift is not just c, it's c divided by b. You've got to imagine the x being factorised. And if we were to factorise out, I would get b outside of x minus c over b. The phase turns out to be c over b. Oh, it's also an odd function, that's very useful. So we know the sine of minus x is equal to the minus sine of x. That's a little feature that can be used when solving trig identities, all sorts of things we can use that for. Let's go crazy. We're going to draw y equals 5 times the sine of 9x minus pi on 2. How would I approach this? Obviously I know it's the basic sine curve. I want to work out its period, so then I know where to mark off my points. It'll be 2 pi divided by 9. So there's our period. Amplitude, how far up, how far down does it go? Well, it's 5 units, the coefficient there of the trig function. I will mark my divisions every pi on 18. That's 2 pi on 9 divided by 4. And there is a shift happening. I've shifted it pi on 18, because it's pi on 2, but divided by the 9, pi on 18 to the right. That gives me enough information to draw my trig curve. So let's put in some axes and mark in some points. We know it's going from 5 to minus 5 there. And you'll notice I'm essentially drawing exactly the same picture I drew before. I've just changed the labels. So it's now pi on 9, 2 pi on 9, and minus pi on 9, and 5 minus pi. Now I'm just drawing a basic sine curve, same as I did before. I'm going to start at the origin, but oh, hang on a sec. You'll notice I didn't start at the origin. Why? Because I've got the shift. So instead of starting at the origin, I've shifted pi on 18 to the right. That's where I've gone. Then the pattern. I know it goes up, but then it goes down and up and down and up. And we draw in our curve. and there's 5 sine 9x minus pi on 2. So essentially you draw the same graph every single time. It's just what the labels are. Cosine then, let's remind ourselves of cosine. I'm not going to draw the whole thing again, but it would generalise to be a cos bx minus c. Its period would also be 2 pi on b. Its amplitude is also a, because remember, the sine curve and the cosine curve, they're essentially the same curve. All the cosine curve is the sine curve, it's been shifted 90 degrees or pi on 2. That's what the cos stands for. It's the complementary ratio to sine. If you remember complementary angles from geometry, they add up to 90 degrees. So that's where the word comes from. Divisions, again, I will mark off every period divided by 4. The phase is the same, c on 4. But this one's an even function. Cosine's an even function. So that tells me the cosine of minus x is equal to the cosine of x. All right, let's do this one, speaking of going crazy. Minus 4 cos x on 8 plus pi, plus another 2 for the heck of it. My period, 2 pi on 1/8, 16 pi. The amplitude is 4. We don't say negative 4, because whether it's negative or positive there doesn't matter, because we're going up and down. So we just say, oh, it's 4 units, whatever, 4 units. That's the distance we're talking about. The divisions, I'm going to mark off every 16 pi divided by 4, that's 4 pi. Now, we've got some shift happening here. The shift is going to end up being pi divided by 1/8, which is 8 pi. And it's going to the left, but we've also got this plus 2, so it's also going to go up 2. Oh, but hang on, I've got a negative as well, so I've also got a reflection. It's upside down as well. Let's draw some axes in. Now, because I've shifted it up 2, and the axis is quite important when it comes to plotting points, I've drawn in a dotted line. I hope you can tell that that's dotted, not solid there, to indicate, hey, this line is not actually part of the graph. I'm just going to use it to help me draw this curve. And it's at 2. We've shifted up 2. Now, the amplitude we said was, where is it? There it is, 4. So I know I'm going up to 6, down to negative 2. They're going to become important. My divisions, I'm marking off every 4 pi. I think we've got enough information. Cosine curve, where do I start? Normally I would start at 1, or the top of the amplitude, but hang on a sec, this one's upside down first, so it's upside down. But then I'm going to get that point, I'm going to shift it 8 pi to the left, and then up 2. There we are. It then goes to the axis, and then up and down and up and down, and we have our cosine curve. There it is. So it's an upside down cosine curve being shifted around. Well, it wouldn't be complete unless we looked at tan as well. Now, there's tan. This one's a little bit different, because remember, the tan curve has a period of pi, or 180 degrees, not 2 pi. So in our general one, it'll be pi divided by b, not 2 pi divided by b. You'll notice I didn't bother with the amplitude, because the tan curve goes up to infinity, down to minus infinity, so it does not matter what we stretch it up by or push it down by, it's still going to have the same range of minus infinity to plus infinity. It has no amplitude. The divisions now will be the period divided by 2, because think back to the basic tan curve, there's only 2 boundary points, because we're only going from 0 to pi, not to 2 pi. So I'd only divide this one by 2. The phase is still c on b, that hasn't changed. It's an odd function. Tan's an odd function. Tan of negative x is the same as negative tan x. We will draw, here we go, y equals e tan pi x minus 2 pi. My period will be pi divided by pi. Oh, it's just 1. Period is 1. The divisions therefore will be a half. I will mark off every 1/2. I have shifted 2 pi divided by pi, which is 2, to the right. And that's all I need. So here we go. Mark in those divisions. There they are. Now, the pattern of a tan curve. Tan curve starts at the origin. Hang on, we have shifted 2 to the right. So I will start at 2. The pattern for a tan curve goes x-intercept, asymptote, x-intercept, asymptote, x-intercept, asymptote, and I can keep going. So let's do that. There's an asymptote, go back the other way, asymptote, x-intercept, asymptote, x-intercept, asymptote. There it is. Now we draw in our basic tan curve, which looks like that. It bends towards the asymptotes. The thing to be careful with the tan curve, it is not a cubic. Do not draw a horizontal point of inflection there. It comes through at 45 degrees. Okay, so it comes through at 45 degrees. And that gets repeated between all of the asymptotes. The E, you notice, I didn't even consider it because I have no scale on my y-axis, so it doesn't really matter. I could have put any number there, I would have drawn exactly the same picture. It only would matter if I was putting two graphs on the one, and then possibly the y-scale would matter. Last year's HSC, they were presented with this trig graph, y equals some constant times the sine of AX. They simply wanted to know what are the values of K and A. So in other words, what sort of dilation is happening here? Well, I can see that the amplitude straight away is 4. So that gives me K quite quickly because I know the coefficient of the trig curve is the amplitude. Is it upside down? Is it the right way round? I suppose is the only question we have to ask ourselves. But it looks like K is 4. The period is 6 pi. So here I am at the origin. It's always good to use 0 because it's a nice reference point. And it's going up at the origin. It's not until we get to 6 pi it's going up again. So I know the period is 6 pi. Well, hang on. The period is 2 pi on A, coefficient of x. Therefore, I can play with that and I get A is 1/3. There's our answer. A is 1/3, K is 4. So you didn't actually have to draw anything on this one. I guess this question was more drawing out, do you understand what's happening with the dilations here? How does it work? Okay, 3J.